Good morning, everyone. Thanks for coming. I'm very happy to be here. It's my first quantum conference in the Philippines. Um, could I have my slides, please? I'll just okay. My slides, please. Okay. Oh, great. Okay. So when Bobby asked me to come here, the first request was to talk about women in quantum. But I thought that's not a problem here in the Philippines because actually we have a lot of women in physics and women in quantum physics. From this conference, you could see we are at about 30%. If you look at the American Physical Society Division of Quantum Information, that would be optimistically around 10%. So I think that's something that we have to take advantage of here. I'm going to talk about frontiers in quantum research. That was the ask. But I want to come here as a physicist. So I want to talk about what is quantum in the year of quantum and really just what I find interesting. So I hope you will humor me and listen for the next 30 minutes or so. Um, Before I begin, I'm going to thank my sponsors. My research has been funded by the Australian Research Council um, and the Westpac Bank, which is one of the 4 largest banks in Australia. So if there's any banking people here, let that be a lesson to us. And of course, L'Oreal UNESCO Foundation for Women in Science. Okay. Um, we've heard community said in this conference a lot of times, and this is one of the main messages I want to convey. It takes a community to raise a scientist. I am one of the scientists that has been raised here in the Philippines. I got my scholarship in Philippine Science High School many, many years ago. I'm a Y2K graduate, so I know what Y2K is. I went to the University of the Philippines. I did an applied physics and master's in physics degree. And then I went to Hogwarts in the University of Glasgow, where I did research for 7 years. I am now based at the University of Queensland, where I had a group called QDITS at UQ. I'm going to talk about that in a while. That's our website, quantum@ibapa.org. At Ibapa is like the Filipino version of etc. So I talk about quantum and many other things. So the main messages I want to give in my talk is one, quantum is not magic. It's really not, it's one of the things that annoy me when I go to conferences and people say quantum and magic in one breath. We are all fascinated by magic, but we don't want to be magicians. So I think that's really important. Quantum is physics. It is just physics. Whatever trouble we have in understanding quantum is not in the physics, it's in our heads. And I think that's one of the shining moments in my career was in the opening of the Quantum Year in Paris, and Sir Peter Knight said just that, and quoted me, and that was really wow, that's really good. And lastly, I want to say quantum is enabling, and not just quantum computing. There is a lot in quantum that's not computing, and I want to talk about those things today. Now, one of the controversies, issues, whatever you want to call it, is that there is a divide between quantum physics and classical physics. You will find various positions on this question. My position is that I don't think there is a divide. There is just a useful theory and a not useful theory in any particular situation that you will encounter. And to me, quantum is like that. There is only information, and you can treat it like classical information or quantum information. It's in the way that you have information. One example that surprised us in the very beginning of the history of quantum physics is this problem, the box potential problem. When you have a particle in a box, do I have a laser pointer? Okay. When you have a particle in a box with a red dot, you ask the question, in this box with the infinite potential represented by the black lines, where will the particle be? And the classical answer to that is that it can be anywhere in the box. But in quantum mechanics, actually the answer is that, well, it can be only in where you have the amplitude, where amplitude is not zero. So particularly where the function is zero, you will not find the particle there. And it's more likely to be where you have a lot of the wiggling, like in the nodes and the antinodes. So there you have maybe one of the differences that was discovered was that you have these questions with different answers in classical and quantum mechanics. And my friend Chris Ferry wrote a book about it, Quantum Physics for Babies, where he talks about this forbidden energies. So at the bottom of it all is information. And this is maybe one of the most profound realizations that I've had as a young scientist here in the Philippines, that information is physical. And the rules that you apply to information really depend on the physical system that you have. So maybe the young people here would know TikTok, Facebook, Instagram, whatever. Those are information in physical systems. And you might have done this experiment yourself when you were young, the telephone using cans and you've got the string vibrating. You hear the voice of your friend. That's one example of analog information carried by a physical system. Now, our information systems is based on the bit. So we have the wavy thing that we've discretized into the 0 and 1. And that's the basis of our classical information, 0 and 1. The bit, which is the simplest classical system, heads or tails. And here in quantum information, we've got what we call the qubits, so spin +1 -1. If you want to think of a physical system, you could think about the way that the electron is spinning. So that's our qubit. Where should I be pointing this thing? Okay, qubits. Okay. And what's so special about qubits is that, one, there is no way to measure a qubit without affecting its state. And this is, the measurement problem in quantum mechanics, which up to now is, undecided, very active debate. Mathematically, qubits are represented by a different mathematical object, and they are represented by complex numbers. Raise your hands if you know what a complex number is. Great, okay, because all this time has been just leading to this. So complex numbers, they have a real and imaginary part, just like life. Okay, that's your first joke for today. We have real and imaginary parts, and really, to me, that's the difference. You have complex numbers with interference that you can control using your physics instruments. Okay. I started in quantum by Googling quantum because I heard my physics teacher complain about quantum. That was a long journey because there are a lot of articles that are actually not correct. Recently, I have found this book, Quantum Mechanics, the Theoretical Minimum. So if you want to have a go at quantum, I'd really encourage you to read that. I will not have time to talk about entanglement, but we're probably familiar about it. And if you are a professor teaching quantum mechanics, I just show you here where quantum mechanics starts, usually the hydrogen atom energy level, and strongly discourage you to start from that because that is really boring. Entanglement is where we should start. Okay, we have heard a lot about quantum technologies, so I will not talk about this a lot. I just picked some experiments that I thought are remarkable and to me as a physicist was very impressive. So the first one was the quantum key distribution intercontinental. So intercontinental between Europe and China back in 2017. This was ground station to satellite and back. That was the most secure video call back in 2017 at kilobyte per second rate. That's Anton Zeilinger there at the right. He's a Nobel winner. But more recently, this experiment was even broken. The record was broken. So now our record for intercontinental quantum key distribution is at 12,900 kilometers between China and South Africa in Stellenbosch. So South Africa, Stellenbosch. Um, I don't think you would think of South Africa as a leader in quantum physics when you know, look at the world, but you really can see that with willpower and expert talent in a country with other problems, you can do some really impressive things. And I hope we take inspiration from that. So what's impressive about this experiment is that they got rid of the ground stations. They have portable optical ground stations instead. So you could actually drive them in a truck or something. So you can change where your ground station would be. And instead of using the MISHUS satellite, which was a satellite commissioned by China to do quantum information in space, they use microsatellites instead. So you have a 10-factor reduction in the payload of your satellites. I mean, maybe Spectral will do something like that. Okay, quantum sensing. So we heard a lot about choosing problems that resonate with the community in your country. And this is one Australian example because Australia has a lot of mining. Like it's a resources intensive country. So one of my colleagues at the university was proposing this quantum way bridge where they'd actually use clouds of atoms, you know, so you'll literally cloud of atoms, you'll ask the truck to drive by it. And with the distribution of the atoms in that device, you could have very precise measurements of the weight and the mass distribution carried by that truck. So apparently, mining companies are very interested. Okay. So now I want to talk about quantum computing, but from a very physics cautious perspective. I think Julian really described it very accurately yesterday. Quantum computers are not just faster versions of classical computers. The provable advantages are for very specific problems. And we already know these. You've got advantage for Shor algorithm, which is factoring large numbers, and Grover algorithm, which is finding an item in an unsorted database. So when physicists talk about advantage in quantum computing, usually we refer to a scientific advantage, like a provable advantage that I can prove using theorems and all that, using complexity theory. And often we are looking for exponential speedups or some polynomial speedups. We talk about the advantage in terms of exponential, quadratic, etc., which is very different from the way that quantum advantage is used in literature these days. Okay. So I want to share my thoughts about quantum computing in general because I know there's a lot of work here and internationally. Quantum advantage for optimization problems are inconclusive. And when I say inconclusive, there's no provable advantage in the way that Shor and Grover has. But as Julian said, there are advantages maybe in terms of 1%, 2%, 3% improvement. So there's maybe financial advantage there. Classical algorithms are often better for convex optimization. So when you have a function with many minima, there's no proof that a quantum computer will be better there. There's a very hot area right now, which is quantum machine learning. So this is using a quantum computer to perform machine learning. Are there advantages there? And my thoughts are, and I think many quantum machine learning people agree as well, machine learning in itself, like using deep neural networks, is very hard to understand. It's a neural network. And if you're gonna claim a quantum advantage that, if you run that in a quantum computer, to me, the premise is that you understand machine learning first. And that's not true. We don't understand it. So it's hard for me as a scientist to prove that running that in a quantum computer will lead to an advantage because I don't understand this thing. So I think we just have to be cautious. Um, it's very challenging. And this is one of when I was a 15-year-old Googling quantum, I read an article that a quantum computer can solve the traveling salesman problem efficiently. That's not correct. Traveling salesman problem is an NP hard problem. The advantages for quantum computing lies on the BQP, BPP space. So I think there's a lot of complexity theory that we need to figure out before we can claim that thing. So what am I getting at? Quantum is physics. You know, whether quantum computing will change the world in the next 10 years, in the next 20 years, is maybe not as relevant as using quantum physics to understand the world. And I want to go back to, what Feynman said in 1982, which started quantum computing. The world is quantum, nature is quantum. So if you have some system that's described by quantum physics, you use a quantum computer. And that's really an interesting problem and a very hard problem. And 1982, come 2000, who's heard of the DiVincenzo criteria? DiVincenzo criteria, okay, a few of us. So the DiVincenzo criteria is what do you need to make a quantum computer? So I'll give you a moment to read that while I. We read it, there's gonna be a wait. Okay. So if you look at that, you can divide the criteria into three things. So first, you have to be able to generate your qubit and specify what state of the qubit you want. You need to be able to process that qubit in the way that gates process bits. So that's the processing part. And then you've got to have measurement and detection. The last two actually was not in the original DiVincenzo paper. That was added later on, but I think it's very relevant these days because especially now we are realizing that we cannot have a useful quantum computer in one system. We are going to interconnect our chips, and that is good if you are a photonics people like me because the most effective way of connecting chips is by using photons. That's what our quantum internet is based on. Before I go to what I actually do, I think I have 15 minutes left in my talk. I wanna talk about the difference between a matter-based and a photon-based computer because I find when I talk to people, we have different languages because we just have very different systems. So I wanna identify what are the differences. So matter-based, example, superconducting qubits like IBM, Google, spin, ions, neutral atoms. So those are matter, they're matter. The qubits are fixed in place. You fabricate your qubits, they stay there. And then the computation happens as time-dependent controls like signals are fed into the system in a particular order that your physicist has computed. And then you're able to solve your problems using that. So it's very similar to a conventional silicon computer. Okay? Now, a photon-based computer is different. So photon-based, there are two main examples. So photons like psi-quantum, or measuring an electromagnetic field like Xanadu does. Here you have pulses of light that are moving through optical fibers or waveguides. So your qubits are actually moving in your system. And you use entangled qubits to do the computation. You have to continuously create them because you are continuously measuring them. So it's actually, it doesn't look like a conventional computer. It actually looks like an optical network. So when we are benchmarking a quantum computer, often we talk about how many bits do you have? How many qubits do you have? If you're a photonic person, that doesn't make much sense because are we talking about the photons that I have generated in the whole time of the computation? It's it's very different. Often we talk about how quickly can we generate the entangled states, and how many entangled states we need to generate depend on what we are doing. So it's very hard to benchmark. So I mean, just be wary when we are comparing quantum computers. Now, quantum computers of both types exist. They are not useful at this time. This is one example of a use case. I did not bother to find the name of this molecule. Let's call it E32. Okay, it's got 119 atoms. And if you want to solve the configuration space of this molecule, you will find that with current 2025 technology, you will need more than a decade and 10 million upwards physical qubits in order to solve that. And in order to, I mean, what we are saying is that in order to make that economically viable, you have to be somewhere around this or this pink region here. And how do we get there? One, we need high performance qubits. So when Julian said yesterday that it's an engineering problem, it is an engineering problem once you have chosen your qubit. You make your roadmap and you engineer your way to that. What I'm saying as a physicist is that you can start with a qubit that is better. If you think about the bit error rate of a classical computer, who knows what the bit error rate is? Like the probability that a high voltage will become a low voltage in a classical computer. Yes. What's the? Somebody's raising their hand. What's the 10 to the minus 18? Okay, 10 to the minus 18, correct. So 10 to the minus 18, that's like the number of grains of sand on Earth. And 1 in 10 to the 18 bit will flip. Okay? It's very good, very reliable. What is the qubit error rate of the best superconducting qubit? It's, depending on who you believe, it's like 1% to 0.1%. Okay, 1 in 1,000. So we are orders in magnitude away from reliability that we have as a classical computer. So as a physicist then, my question is, well, can we find a better qubit to start with? And so you see, it's not an engineering problem to me. Another thing that we need is resource efficient logic. The number of physical qubits that you need for a logical qubit will depend on the error correction that you have. For a long time, we thought that was the surface code, and now we're all going to LDPC. I'm not an expert, I'm just throwing these terms to you. But what I'm saying is, there is a big space for quantum error correction that I think we still need to explore. And then lastly, I don't think we have figured out how we will interconnect these computers. Like superconducting quantum computer, you control that with microwave, you have microwave photons. If you're gonna have a distributed quantum computing network, your best bet will be photons because we already have optical fibers. We have figured out these optical infrastructure. So it makes sense to convert microwave to optical, and that's a very hard physics problem. So there is a lot of science, I think, and there's space for a lot more people to work in the field. So at UQ, we're QDITs at UQ. I'm going to talk about QDITs. QDITs. What are QDITs? So this is a qubit, 0 and 1. I use particles of light, in particular their shape. So like you think about the intensity distribution of light. That is my qubit. And the nice thing about that is that I can do dead and alive cat, but I can also do dead and alive chick or whatever you like. because I can control and prepare different shapes of light. So I have qubits, dual rail versus D-rail. And it's very niche, like at this point, that's the Google Trends. Um, my group started there, so one of our tasks is to Google qubits so that I can have graphs like this to present in talks. Qubits is like this, so you see there's a lot of work to do. But I think it's a very interesting system to work with because one, you start with a higher information capacity. If you just think about how many orthogonal states can you represent with 10 qubits, you can, if you have 10 qubits, that equivalent would be 232 level qubits, right? And another thing is it's more robust. Like in quantum mechanics, we do not have a quantum photocopying machine. That's the no cloning theorem. But you can do cloning if you are prepared to accept some failure. And the failure rate actually becomes higher as you go to higher dimensions. So it gives you extra robustness against that. If you're doing QKD, QDITs give you higher error thresholds. So it makes sense to use QDITs. So as a scientist, I am interested in what can be done only with QDITs and what can be done only with QDIT entanglement. Because I think I don't want to compete with, better than that, better than that. I want to do what can you do only with QDITs. I've written articles about it. I can give you a copy of this one. I'm giving you this. It's a Lord of the Rings kind of map for entanglement in higher dimensions. I think it's really interesting. It's very different from qubit entanglement. Okay, I have 5 minutes left. Do I have 5 minutes left? Yes? Okay. So in my group, we work on transverse mode, so the shapes of photons. So that's you can, if you think of photons, you can think of color, the path that they take on your chip, the time that they arrive on your detector. In our group, we work with transverse modes, the photon shape, because it introduces some parallelism and maybe not as much complexity. Um, in order to work on that, we need to design some new devices. And when I say design new devices, that's because I don't want to do this. So this is a multiplexer for transverse modes. As you can see, it's very carefully tuned so that you've got the exact width, the exact length. It's tedious. In our group, we do photonic inverse design instead. So photonic inverse design is an optimization. It's machine learning for for photonic chips. It was the package that we are using came from Stanford University from the group of Jelena Vukovic. And here, the nice thing about it is I don't start from the physics. I start from the function of the device. So say here I have a 3x3 piece of silicon, which I want to have some inputs and some particular outputs. I design a cost function for it and then let the algorithm run. And here we're trying to do a multiplexer. So like we're just TE0 and TE1, like those two shapes will go together in that one output port. And you see we have very good performance here and we can fabricate them. This is for the physicists in the room, but maybe there's not many. So we tried this very weird looking device in an actual quantum experiment. I will not have time to describe what the Hong-Omandel interference is. It's the hallmark quantum optics experiment from the 1980s. And we did that in our inverse design devices. We asked for some very good photons from our friends at Griffith University. And you don't have to understand the details here. What I want you to focus at is that there is a number there called the visibility, which is 99.56%. A good quantum experiment will have that as 100%. And we are able to achieve 99.56% with those inverse design devices. And we can do it reliably. So like this right figure here are just different iterations of that device, and we showed that we could actually get 99% very reliably. So I want to leave some time for questions. So I just end with this message, which I'll just reiterate. And I'm going to thank you, share you my photos of the Nobel winners from 2022. All my photos, by the way. I've met them all. I can tell you the interpretations that they ask, that they favor if in question time. Okay, thank you.
Thank you so much, Dr. Romero. So, are there any questions from the audience?
Promised you a question, so thank you for so casually putting D-Wave out of business the first 10 minutes. You made me very sad. You said quantum is not magic, so I'd like to challenge you. 40 years into the future, you're probably at the end of your quantum career. What do you think is the most fun and coolest thing that quantum will have delivered by then?
So there is, can I give you two answers?
Yes, please.
Okay. One is very philosophical. Like what attracted me to this field is that you've got the philosophical tension and the really enabling technology. 40 years from now, I don't know how it will happen, but I hope we have a better idea of what interpretation of quantum mechanics is I don't know, most likely, or maybe it's figured out what interpretations of quantum physics. The other is that I really hope that quantum has changed the world. Like, I really hope that we will discover E32 and figure out today what we will do when we have E32. Because I think our only shot of discovering those catalysts for greenhouse emissions, carbon capture is a quantum computer. I truly believe in my heart that is true, but I don't know how we get there. But maybe 40 years is enough.
What's the substrate that you use on your chip?
We're using silicon at the moment, probably moving
28.
to silicon nitride, and I'm trying lithium niobate as well.
Any more questions?
Hi, thanks for the talk. I have a semi-physics question. You mentioned a lot about, you mentioned a little bit about qubits, but I feel like that's half the story because I don't believe there's free lunch in the world.
Oh yeah, exactly.
So what's are the bad things about qubits?
Yes, of course. I will go to, I'm going to go to a specific example. So Psi Quantum, which is a very big photonic quantum computing company that is backed by $1 billion investment in Australia, they need to entangle photons. The entangling success of qubits is 50%. Like there are theorems, it's 50% max. You can do higher entangling probability success with qubits. But the problem is you have to carry that advantage all the way to the end. So meaning when you do your decoding, when you do your measurement, you have to carry that advantage. And so far, I don't think we've figured out how to do it. I don't think it's impossible, but it is a hard problem. Yeah, so that's the catch. Higher entangling probability, but maybe harder to measure it as well.
Okay, thank you so much. I think I can accommodate one more question. Anyone from the audience? Okay, so I have a question, Dr. Romero. So I think this is a controversial take. So what do you think about people saying it's not important to take up quantum mechanics in understanding quantum computing?
In order to do quantum computing, if you want to use it, design algorithms, do error correction, the maths is really not, I think you can do it without really immersing yourself in all the foundational questions of quantum mechanics. Because, it's linear algebra, tensor algebra, SUD, that's all mathematics. In order to appreciate it, like to really be affected by it in maybe the way that I am, I think you need to understand it. So like I often tell my group, I am a quantum physicist, quantum engineer, I think about the foundations of quantum mechanics on weekends, like the romantic side of it, which is also very fun. I think you need to understand that in order to appreciate it. To make something useful, you need to understand not just quantum physics, like you need to understand optics, you need to understand how waveguides work, like it's the more you know, the better you can do. But if you just want to use it, like I think maths is enough.
Thank you so much, Dr. Romero. And I think that ends our Q&A session for Dr. Romero's session. Let us give her a round of applause.